Hello, my name is Andrew Edwards. I work at Fisheries and Oceans Canada, just over there. And this is work I've been doing with Kerry Holt and Luke Rogers. The motivation for this work comes from this paper about 5 years ago concerning a technique called Empirical Dynamic Modelling, or EDM. And the conclusions of this paper were that EDM models produce more accurate and precise forecasts and yield significant improvements, unlike the traditional Ricker-type models that people use to, in particular, to model and manage Fraser River sockeye salmon. However, these methods are not commonly considered in an operational sense, and they're not being used to provide advice for managers. So our question is, should they be used? So here I have a simple simulation of a salmon population. And on the top left, we are plotting just n, the number of the population size at time t against t. And you can see a time series going through in time. The bottom left, we have the first difference of that, which is xt, which is the difference between the nt plus 1 and nt. And you can see that's evolving as well. Another way of plotting the same data is on the top middle panel, which is a phase plot of nt against nt minus 1. And the bottom shows a phase plot of the x values, the lagged values. As you can see, with these x lagged values, there is some structure appearing in this phase plot. Now you can do a phase plot for more than 2 dimensions. So here's one for 3 dimensions, showing xt, x at t minus 1, and x at t minus 2. And as you can see, again, there is some kind of structure. And the idea of EDM is that you can do further plots in lag space with higher dimensions, known as the embedding dimension, which is called E. And with different values of E, you can see how well the predictions you make fit the observations. So how does it work? Showing the 2-dimensional version, we pick a point, at say time step 39. This is all the points in the lag space. We want to start from this point, and we want to predict where that value will go at the next time step, value of x40. So what you do is you pick your 3 nearest neighbors in space, so not time, but the nearest values in the phase space, and project forward 1 step in time to see where they went. And then to estimate where this the blue dot will go, you take a weighted average of those 3 resulting values. And that gives you your prediction for x at time 40. And there's a package called REDM. And for this example, the results agree with that. And it's actually close to the true value in green. And we know the true value because we've simulated the data. However, when we did our own code to understand this better, we found some issues with the REDM package. For example, if we know the x value at time step 39, we want to predict x value at time 40. So write this as a vector in this format. You have this x39 and x38. To predict the x40, you need to predict x40 and x39. But in that nearest neighbor sense, we found out that REDM allows this value, which includes x40. So the vector in the phase space includes the value that you're actually trying to predict, which does not seem ideal. So we've started our package, tailoring for our own needs in fisheries research, and verified it with independent code. And we are planning to get some results over the summer and this September. So thank you for your time.